So if not, let us dive into the nitty-gritty of group theory. So let's start with what I'm going to call fundamental concepts, okay? Okay, so let's start with the definition of a group. Okay. Let's just say. So what is a group? So a group is a set, say G, equipped with a binary operation. We'll just call it circle. Now this binary operation is usually known as the group composition law or the group multiplication. I'm just going to call it the group multiplication, or in short, multiplication. And this is not your everyday multiplication. It just shares that name. It may or may not be. So, okay. Group multiplication, and which has the following properties. Okay. Number one is that it's a closed set under this multiplication. So it's known as closure. Sorry. Closure. So that means that if A is an element of that group and B is also an element of that group, then A times B is also an element of that group. So this is what we mean by closure. Okay, so note that the set itself is not group. The group is G, the set, along with the multiplication, which has the following properties. It's closed. Number two, the multiplication is associative. So associativity. So suppose A, if you have multiplied A and B and then multiplied to C, that's the same as A first multiplying B and C and multiplying A with it. So the group multiplication is associative. Associativity is a very nice property. One can do without commutativity, but it's very hard to do do anything without associativity. Number three is that there must exist a unique element which we call the identity. So what is the identity? So there must exist a unique element let's call it E. It's called the identity, or identity element, in short called identity, such that for any group element A times E is going to be A. For any A in G. Okay, so with the next axiom, next postulate, we will be able to show that if E satisfies, E is, you know, the way I define E, it's better to call it right identity, right? Because it's multiplying A on the right. But with the next axiom, one can show that if the right identity exists, it also satisfies this. So the identity is actually satisfies this for all A. Okay. So the right and the left identity are the same. So this will be probably one of the homeworks I'm going to give you. So that was number 3. Number 4 is that inverse. So for each group element, G, small g, there exists a unique element, G inverse, such that G inverse is the identity. And if this is the case, you can also show that G inverse of G is also the identity. In other words, G inverse is equal to G inverse G is equals to E. Okay. Now, any questions?
No, sir. Sir, right identity আর left identity এই দুইটা যে সেম হইতে হবে, এটা কি মানে অ্যাসোসিয়েটিভিটির কারণে এটা হইতে হবে?
You have to prove this. So this is one of the things I'm going to tell you.
Well, they are not necessarily equal.
They are equal, yes. That's actually a proof that I'm going to give you, okay? For a group, they are equal.
Yeah, for group, but I was thinking something else.
Yeah, well, we are not doing something else, so yeah. Yeah, okay. Any other questions? So, that's something you will have to prove. So, I don't want to, you have to play with these axioms and prove that. So the idea is that, so Moon is going to be the TA for this, ST for this course. And the idea is that every week I'm going to give out some, some exercises in the class. I'm not going to write it up. So you have to be present in the class to get those exercises. And then you have to work those out. And then you have to submit them to Moon, who will then check them and give you feedback. Okay? And why am I doing this? Because I know that a lot of you don't have, like, I don't know, background in abstract algebra. I don't either. I've never taken an abstract algebra class. But, so these kind of proofs that, that one has to do in group theory, these are new things you have to learn. It's easy, but it's new. And there are logical missteps that any one of us can make. So I am just like, by making you do it and submit it, it won't be graded, but by forcing you to submit it, I will be hopefully, forcing you to learn these new tricks, okay? So before I give you the exercise, let me make some comments. Yeah, the left and right inverses are equal, meaning that they're the same element. That's the first thing you have to prove. And then the left and right identities are also equal, so the same element. Okay. Number two is that G inverse, doesn't need to be, say, different from G. And we'll see examples where that's the case, where that G inverse is actually equal to G. Okay. Number three is that it's very cumbersome to always write, say, A times B in that way. So instead, we shall use the notation AB, okay? So in the context, it should be clear that there is a group multiplication, okay? Number four is that the associativity, so which is, say, A, B times C is A, B, C. This is a property of matrices, a property of matrix multiplications, okay? And indeed, groups and matrices are very deeply connected. The fact that matrix multiplication is also associative makes it a natural way to realize groups. Okay? So although associativity is there for group, in general, groups do not satisfy AB equals to BA for all AB in a group. So if AB is equal to BA for all elements in the group, we say that the group G is an abelian group. Okay, this is named after Abel, who was a famous Norwegian mathematician. Okay. Otherwise, the group is called non-abelian. As you know, that matrix multiplication is non-commutative, so that kind of fits in with the non-abelian nature of groups in general. Okay, so that was number 5. So number 6 is that a group may have finite number of elements, finite or infinite number of elements. Okay? And if the number of elements is infinite, it can have countably infinite, or uncountably infinite, or let's just say continuous. Well, let's say uncountably infinite, number of elements. Okay, so it can be anything.
Or does real number make a group?
You have to tell me what operation it is. What is a group multiplication?
Also,
what-
group includes an operation.
Yes, that's what I said, right?
So real number multiplication.
No, it doesn't form a group.
Okay.
And think why. Okay,
Yes, sir.
yeah, think of it. That's a very good question. Okay, let's do an example.